In the previous video, I introduced the N-channel transistor that's shown here at the left. Now I want to introduce the P-channel transistor shown at the right, and then talk a little bit about both transistors. Now notice that the green is an N-type material. For example, this N-channel has a N-type source, an N-type drain, and a P+ region that makes good contact to the P substrate. And notice that the P channel has a P-type source and drain, that it sits in an N well, which is a deep N diffusion. If we didn't have that N well, the P channel source and drain would short out to the substrate, to the P-type substrate, and it wouldn't work. So when the N-channel transistor source and drain are formed, a region of N+ is put in here to make a low resistance contact to the N well. Now recall that whenever we have an N-type material that is adjacent to a P-type material, we have a silicon diode, we have a PN junction. Now let's view those junctions. So shown in red are these diode junctions. For example, here we have a diode with a P-type and the N-type forming a PN junction. Now in the P channel we have a diode from the drain and from the source to the N well region. And over in the N channel we have a diode from the P-type substrate to the drain and to the source region. Now it is very important that these diodes never become forward biased. So that is why this substrate will be tied usually to the most negative potential. Here is tied to 0 volts or ground. So as long as the source and drain on the N channel do not go below ground, we're okay. This diode and this diode will not become forward biased. Now in the P channel, we'll usually set the well at a high voltage. Here we've set it for plus 5 volts. So the N well to the P-type substrate diode, this diode here, is reverse biased by 5 volts. So this diode will never become forward biased. And also we never want the drain and source diodes to become forward biased. Therefore, we never want the P regions of the P channel to go above 5 volts. If that happens, we're in a lot of trouble when we forward bias these diodes. So let me turn off this view. The operation of the P-channel transistor is very similar to the operation of the N-channel transistor. If you understand the N-channel operation, you really understand the P-channel operation also. Except on the P-channel, the voltages are reversed from the N-channel. And of course, looking at the structure, you see that the P-types and N-types are reversed between the N-channel and the P-channel. So let's review the operation of the N-channel transistor and compare that to how the P-channel works. So if we have the source voltage, say we set it to ground. This is my ground symbol, or 0 volts. And we increase the gate voltage. Say we increase the gate voltage by a certain voltage we call V threshold. And that's the critical voltage at which the strength of this electric field under the gate is just enough to start inverting this P-type region to an N-type region, and thus getting conduction between the source and the drain shown here. Now, as we increase the voltage at the gate, this electric field becomes more intense, and we drive this channel region down further. Now, a similar thing happens with the P channel, except the voltages are reversed. So instead of having the source at ground, we're going to have the source at a high voltage. We're going to have this at plus 5 volts. And we're going to have the N well also at plus 5 volts. So our source to N well diode does not become forward biased. Now, as we decrease the P channel gate voltage relative to the source, say we make it more negative by, say we set the gate voltage at 4.3 volts. So that produces an electric field in this direction. So the electric field is from the positive voltage to the negative voltage. And at this point, the gate voltage is more negative by about 0.7 volts. And let's presume that the threshold, the VT, is 0.7 volts. So our channel inverts at the surface here. It changes from an N-type material to a P-type material, and we start getting conduction from source to this drain region. Now, as we decrease the gate voltage relative to the source even more, we make this electric field stronger, and that pushes this channel region down further into the silicon. So you can see that the operation of the P channel is very similar to the N channel, that we have a high voltage at the source, where in the N channel we have a low voltage at the source. We cause the transistor to conduct in the N channel by raising the gate voltage, and in the P channel we lower the gate voltage. But the operation's very similar. The N channel actually has a slight advantage over the P channel because there's a mobility term in the channel region that we call mu, and we presented that in a previous equation. And in the N channel, the mobility is greater than the mobility mu in the P channel. So if you have a choice, you could either use an N channel transistor or a P channel. If either one would work fine, you generally want to choose the N channel since it conducts a little better, since the mobility of the electrons in the channel region is better than the mobility of the holes in the P channel transistor. Now I want to introduce the symbols for the N channel transistor and for the P channel transistor. So let's view the symbols on top of this drawing. So notice that the symbol for these transistors are very similar to the structure of the transistor. Here we have the gate terminal, the source terminal, the drain terminal, and the substrate connection. Over on the P channel, this symbol is virtually the same, except I have a little bubble to denote that the voltages are inverted from the N channel case. So here we have the gate, We can call this the source, this the drain, and this is the end well connection. Let's turn off the silicon layers and just view the symbols. So sometimes I find it very convenient to think of these symbols in terms of the actual transistor structure. For example, let me erase that little mark. For example, when I increase the gate voltage relative to the source, I like to think of forming an electric field here that inverts the channel region, and I get conduction between the source and the drain. Now, in a similar way, I like to think of the source voltage perhaps at plus 5 volts, and I decrease the gate voltage to a lower voltage than the source, and I get an electric field in this direction that inverts this channel region and causes conduction between the source and drain. And recall that as I increase the drain voltage, the structure of this channel changes, and the electric field of the drain region decreases, so the channel can become more like this. And sometimes I like to just look at the symbol and look at the different voltages, and in my mind think of how this channel works. And that helps a lot when later you use these symbols to do circuit design.